So this illuminator can go either on your vertical illuminator as a reflected light source, or it can go on the transmitted light source. So what are the benefits of this 4-light LED illuminator? It has 4 lights. So if you look over here on the left, if you have the illuminator, your graphic user interface will look like this. You'll be able to control the 4 lights. You can control all the lights together, just like a regular 2D microscope, or you have the option of controlling each of these pie-shaped illuminated lights either together, left and right together. You can put both right ones together to make a right eye view, both left together to make a left eye view. That'll make a stereo picture. Or you can do individually, set each of these, and that tells you the intensity of the light. So what this illuminator does is it enhances contrast, increases resolution, improves depth of field, and produces real-time stereo 3D. So let's look at this. The first thing it is, it's a powerful contrast enhancement system. And this is really important because it produces highlights and shadows on specimens that allows you to get better visibility, allows you to see it where otherwise you couldn't really see very much. So let's look at this Radiolaria with bright field. This has got all 4 lights on it, basically one standard. This is a bright field image, and you can barely see what's happening. But look what happens when you turn one single oblique light on from the northwest. Now all of a sudden, wow, it's like night and day. Now you can see every little bit of of these little microorganisms with good contrast, and the stacking gives you incredible depth of field. So here's an example closer up. Let's look at the same thing with a higher power lens. So here you can see we have all the lights on. So this is, and when we slide this up, all these other ones, they're ganged together. So all these are sliding up at the same time because you're using them as a single conventional light source when they all go up. So this is what you see. Now, when you go, when you just go, you turn these off and then you just turn on the northwest light, but pulling that up, watch what happens. Now just the northwest light, whoops. Now just the northwest light is on. You can see that light, that is off. This slider is up, all the other ones are off. And now you get a beautiful high contrast, high power view of the Radiolaria. And it will also make the rotational 3D video. So now without glasses, you see all the details in 3D. You see the foreground from the background. So another thing that the 3D illuminator does is it increases the resolution of the lens you happen to be using. And it does that by allowing the objective lens to capture higher order diffraction wavelets. I want to spend just a little bit of time telling you about this. Now, to say that we're going to increase resolution, I mean, we all know that the limit of resolution and magnification was reached 130 years ago by Ernst Abbe from Zeiss. And he came up with the formula of the distance. And this is the minimum, D means the minimum distance between 2 points. That's what the definition of resolution. What is the smallest distance between 2 points that you can still see them as 2 points and not 1 point? Because if they're too small, you only see them as 1 point. So the resolution is 1.22 times the wavelength of light, lambda, divided by the NA, the numerical aperture of the objective lens, plus the numerical aperture of the condenser lens. Now, most people write this formula 2 times the NA, but that doesn't take into consideration the importance of the NA of the condenser lens. And when you use oblique illumination, you can actually increase that, and I'm going to show you how that happens. So here is a picture of a striated muscle cell. This is some, conventional muscle. It's probably taken with a 40x lens, it looks like. And you can see the striations. And these striations come closer and farther apart as the muscle contracts. They're kind of like accordion in a way. Well, if you take the eyepiece, if you're looking at this in your microscope, and you remove the eyepiece out of the right-hand side of your viewing head, this is what you're going to see. You see a diffraction pattern. What happens is, and this was shown by Ernst Abbe 130 years ago, that the specimen produces a diffraction pattern at the pupil inside of the objective lens. So here you can see there's the 0 order of the diffraction pattern. There's the first order and there's the second order. There's the first order on the other side and the second order on the other side. Now here's what happens. As these spacings or distances in the object get smaller and smaller, the diffraction wavelets spread out farther and farther. And at one point, you don't see the diffraction wavelets anymore, and that's when you've reached the limit of resolution. When they say diffraction limits the resolution of the light microscope, it's because you have to see the diffraction wavelets in order to see the resolution. So here's an object that is right at the limit of resolution with a light microscope. This is Pleuristigma angulatum. It's used to test how good your microscope is. If you have a really good microscope, it should look like this. And if you take the right side eyepiece out of the right side, you're going to see the zero order and then the first order. Now, these spacings are so small, you don't see the second order because it falls outside of the objective aperture. Now, notice that I've had to reduce you see the first order? I had to close down the iris of the condenser lens in order to see these wavelets. Otherwise, the zero order would overpower the wavelets. So this is an interesting thing about oblique illumination. It attenuates the zero order so that more information from the wavelets is used. So look at this. Let's get to a diatom that's below the resolution of a light microscope. So this is Amphipleura Pellucida. It's got markings that are 250 by 200 nanometer markings. And if if you're just looking at it with a dry lens, if you're not using a 1.4 Na oil objective and a 1.4 Na oil condenser, this is what you're going to see. You're not going to see any markings. You're just going to see the outline of the diatom. If you use a really good lens, 1.4 Na, and you put oil on the condenser and on the objective, you're going to see these lines. But if you use oblique illumination and you tilt the illumination so that the zero order is out to one side and the first order is out to the other side, you pick up an additional order you pick up the diffraction wavelet for the 200 nanometer markings, and here with oblique illumination, now you can see that those lines actually consist of little dots. Here's an example of the diatom that I showed you that had just one order of diffraction wavelet. So this is the Pleuristigma angulatum. But look, we bring the zero order all the way out to the side, so it doesn't overpower the input from the wavelets. So now you get, instead of just the first order, you're getting the first order and the second order. And if you bring in multiple oblique lights from this direction and from this direction, now you make two diffraction wavelets that interfere with one another that increases the resolution throughout the XY plane even further. So now what's strange about this is not only does it increase resolution, but it increases depth of field, which is kind of counterproductive. Let me try and show you why this is. If you have a setup where you have your condenser lens iris is open, and here's your objective lens, that's going to be the best resolution that you're going to have for whatever you're looking at there. Now, if you close down the iris in your condenser lens, now all of a sudden what happens is you've reduced the cone of illumination and you've created more contrast and more depth of field. The depth of field increased because the F number increased. You see, this is a higher F number than this. So you've increased the depth of field. But look what happens here. If you close down the condenser but bring it over to the side as an oblique illumination beam, now you have the higher F number, so you increase the depth of field, yet you do not lose the resolution. In fact, you slightly increase the resolution via the higher order wavelet. So this is particularly important for live cells. Because in live cells, you can't stain them. You need to see them unstained. And this is the visualization of the closure of the neural tube. I took this picture when I first came across these ideas, and it allows you to see great depth of field and the closure of the neural tube. And the great thing is it does it in plastic dishes without using DIC. People like to grow cells in plastic dishes because they're much more convenient. But DIC uses polarization light, and plastic destroys the polarization. So this is the real advantage for living cells. Here's an example of putting the illuminator on a reflected light source. So here's all lights on. That's just a little bump on a metal surface. Now you use just one oblique illuminator Look, all of a sudden you've increased the depth of field, and now you've created highlights and shadows. You come from a different direction, you create highlights and shadows from a different direction, which allows you to see and understand other aspects of these structures.